Good morning to everyone. I see that there are many people attending this webinar, so we are very happy for that. My name is Fabio Bozzoli. I'm an associate professor of University of Parma. And I just want to introduce Dr. Naoko Iwata. Naoko is a friend of mine, of course, but she's an engineer for JAXA. JAXA is Japan Aerospace Exploration Agency. And now she's in University of Parma thanks to a project supported by European Union inside the Marie Curie Individual Fellowship. So I leave the stage to Naoko. The presentation will take something like 30 minutes. And after there is time, if you want, for questions, comments, as you like. Also, this presentation is going to be stored in our website and on Facebook, and so you can watch it again if you need later. Thank you, Naoko. It's your time.
Thank you. Sorry, thank you for introduction, and ciao tutti. Thank you for attending. The presentation title is Pulsating Heat Pipe and its Potential Application. Today's outline. Before we get into the today's main topic of PHP and its potential applications, let me explain briefly what is necessary. So I mean, what is a heat transfer device and why it is necessary. So recently, thermal management has become a critical issue for industry due to the widespread introduction of microelectronics in almost every processing line. The heat flux and power of the microelectronics devices has continued to increase linearly, showing this left figure. The high operating temperature reduces the reliability and performance of electronics and eventually causes fatal failure. Thus, the efficient thermal management is essential to remove heat from heat sources and prevent heat-related failures. The development of innovative heat transfer devices with high performance, compact, and low cost is now a top priority. By the way, why the heat transfer devices are necessary? If the heat generate device is close to the cooling device, such as fan, it is not necessary. Let's think about the case that the device is far from the fan. Using heat transfer device between them, the heat is transferred by the heat transfer device, and the device can be cooled down. For example, this is the upper figure is inside of the mobile PC. Two tips are not cooled directly by a fan, but through these two sticks. What do you think these sticks are? They are not just metal sticks. They are heat pipes. Heat pipe is a two-phase heat transfer device. Inside the heat pipe, fluid circulates in the gas and liquid phases. When the heat is input to one end of the heat pipe, the fluid evaporates. The vapor moves to the other end that is cooled by the pressure differences. Then the vapor condenses into the liquid. The liquid moves to the heating side by the capillary forces. Capillary force. The inner wall of the heat pipe has a weak structure, such as grooves or powder, which can pump up the liquid. The heat pipe was invented more than 50 years ago. A pulsating heat pipe, we call it PHP, or an oscillating heat pipe, is a new heat pipe invented in 1990s. 1990s. It is the same as a conventional heat pipe in terms of a two-phase passive fluid device, but PHP has a different configuration. PHP consists of a capillary tube meandering between an evaporator and a condenser, and it does not have a wick. PHP is partially filled with a working fluid that exists as a mixture of liquid slug and vapor plug, like this figure. The inner diameter of the tube must be small enough so that the surface tension can overcome the gravity and wet the inner wall of the tube with liquid. Heat is transferred from the evaporator to the condenser by the self-excited oscillation of vapor and liquids. PHP has a lot of advantages: high effective thermal conductivity, large contact area, simple wickless structure, compact and lightweight, and flexibility. PHP can be fabricated with commercially available tubes, so it can be low cost. Despite of the advantages, unfortunately, there have been few commercial applications of PHP. However, a number of potential applications have been proposed so far. I will introduce 10 examples among them. First, most potential application is electronics. This is a test model of copper PHP for cooling electronics. A heat-generating chip is mounted here, and the heat is transferred and spread by the PHP to the heatsink here. In electronics applications, PHP will probably be required to operate not only in a bottom heat mode. It means the fluid circulation is supported by gravity, but also in a horizontal mode. It means there is no gravity assist. And top heat mode, it means fluid should be moved against gravity. In general, PHP performance best in bottom heat condition because gravity assists the liquid to move. The lower graph figure shows the PHP has comparable performance even when operating against gravity. Thermal management is very important for batteries, in particular lithium-ion batteries. Lithium-ion batteries have a narrow allowable temperature range around room temperature. Batteries generate heat during charging and discharging cycle. If the battery's heat is not properly dissipated, it may cause thermal runaway and eventually ignite. As shown in this figure, thin and wide PHP can be suitable for thermal management of batteries. This lower figure shows the temperature gradient is mitigated when the PHP is applied to the batteries. The third is an interesting example that take advantage of PHP's flexibility. This is a thermal test model of a mobile PC with PHP built in. An evaporator is placed under the keyboard where heat-generating parts are located, and the condenser is placed over the entire display. The tubes between them are coiled at hinge so that the PC can be opened and closed repeatedly. PHP can also be made flexible without coiling. A flexible thermal strap is a useful device that combines high thermal conductivity and flexibility. So far, polymetric materials or thin metallic tubes have been proposed for flexible PHP. The four figures on the left show a flow-rubber tubular PHP with microgrooved copper tubes in an evaporator and a condenser. The top right figure shows a polycarbonate-based flat PHP. It is wrapped in a flexible copper-clad laminate. The lower right figure is a PHP composed of stainless steel and nickel tubes with an outer diameter of 0.4 mm or less. PHP can also be applied to devices that are constantly rotating, such as turbine blades and grinding wheels. The left image shows a conceptual drawing of a PHP built in a turbine blades, and the right figure is an experimental setup for it. Centrifugal force can assist fluid flow in PHP. The past study reported that the PHP performance improved with the rotation speed increased. PHP can also be applied to the devices that are PHP can contribute eco-friendly system as shown in this figure and the next slide. Waste heat recovery is an energy reuse system that uses waste heat to warm up water or air. For example, in my hometown, the waste heat from the waste incineration plant was used to warm up the water in a swimming pool. In this system, a heat exchanger between the two loops is essential. A PHP composed of a number of copper tubes has been proposed for the heat exchanger. The evaporator is placed on the hot loop side, and the condenser is on the cold loop side, with the air and water flowing between the tubes. Solar water heating is a system that uses solar energy to warm up the water for daily use. In this system, a large plate called solar collector receives solar heat and warms up the water. The hot water is stored in a tank above the solar collector. The images show a 2.5 meter long PHP proposed as a solar collector. The condenser section is inserted into a water tank. The solar energy is absorbed by 2 meter long evaporator and heat is transferred to the tank. The result of an outdoor demonstration shows a cumulative correct efficiency of 62%. So far, I have presented applications operating in a room temperature or slightly higher, but PHP can also be used to cryogenic devices, such as a superconducting magnet system. For cryogenic PHP, nitrogen, neon, hydrogen, and helium have been selected as working fluid. In these PHPs, the operating temperature can range from few Kelvin to several tens of Kelvin. For example, the image shows a helium PHP and its test result. The evaporator temperature changes from 3 Kelvin to 10 Kelvin, while the heat input is increased from 0.1 watt to 0.7 watt. Probably you are wondering, is there also a high temperature PHP? The answer is yes, there is. For a high temperature PHP with operating temperature of over 500 degrees C, liquid metal should be selected as working fluid. Sodium, potassium, and their alloy could be suitable fluids for high temperature heat pipe. The upper image shows the liquid sodium potassium alloy. The left image shows a PHP composed of a stainless steel tube. Sodium potassium alloy is filled in it. The test result shows the PHP starts up and operates at the evaporator temperature of around 800 degrees C. The potential application of PHP extends beyond the ground to the space. The lightweight PHP is suitable for spacecraft. My colleagues of Japanese Aerospace Agency successfully operated PHP on orbit. The PHP had check valves to induce the flow from the condenser to the evaporator without gravity assist. The PHP was mounted on a small satellite and launched in 2012. The PHP had operated on orbit for 4 years. So this is the summary of this presentation. Thermal management has been a critical issue for electronics due to increasing power and heat flux. Heat transfer device is effective to transfer heat from the heat source to the cooling device. Pulsating heat pipe, or PHP, or oscillating heat pipe, OHP, is a promising two-phase passive heat transfer device with many advantages. 10 examples of the potential PHP applications was introduced in this presentation. So this is a reference list. As Fabio said, this presentation will be uploaded to our website or Facebook or YouTube. So please check later on if you are interested. So for visiting our website, please search with the word of POTPLOS. Thank you for attending.
Thank you very much, Naoko. Very nice presentation. Now we